All right, so we're in this study on reacting mixtures and combustion. And last time we talked about an energy balance statement. Here it is for an open system. So a control volume. What do you have coming in? Some reactants coming in. And what do you have coming out? Some products coming out. And we could have some heat transfer, Q dot, into the control volume, some heat transfer, as well as some work transfer out of that control volume. Often that work is zero. It's a zero shaft work going out. And what do we have? We have an energy balance equation. And then we have, everything looks familiar. It's like the first law. But to make things work for a reacting system, we have to not only have changes in enthalpy, but we have to have an enthalpy of formation. And so that's what's really new, this enthalpy of formation. So let's take a look at it's H for enthalpy, subscript F, not for the saturated liquid. That can be a little confusing. What is that F for? Formation. Enthalpy of formation. We have an overbar. What does that mean? It's on not a mass basis, but on a molar basis. It's kilomoles. And then we have this naught right here. We had some S naughts before, true, so we've seen that naught superscript symbol. What does that naught superscript symbol mean? It's a standard condition. So it'd basically be at low pressure, 1 atm, and at standard temperature. So we go to this table A25 and we look, and here is our enthalpy of formation, and it's emphasized that it's at this temperature and pressure. This temperature is 25 degrees C. It's like the standard temperature atmosphere. And this pressure is 1 atm, standard atmospheric pressure. Now, we introduced this enthalpy of formation so that we could have the first law where you're actually changing. Think about some carbon, hydrogen, fuel coming in. Maybe it's methane. What do you get coming out in the products? The carbon goes to carbon dioxide. The hydrogen goes to water. So it's rearranging the molecules in the combustion. And that's what makes it essential that we have an enthalpy of combustion. Put everything on a level playing field in the energy balance equations. Now, some of the values are zero in this table. Why do they have zeros? Well, they're basically for elements that like to be in that configuration. Carbon as a solid, oxygen, diatomic gaseous oxygen, at that temperature and pressure. It's like, we're happy at this. So those are like stable, considered stable at that temperature and pressure. And then other values are negative. You could just scroll through that table and you'll find some negative values for, let's say, carbon dioxide, carbon monoxide. I just clipped this table, cut it off. And then you have to pay attention. You'll have water and water, that's both H2O, but water could be at 25 degrees C in the liquid state or 25 degrees C in the vapor state. And so you'll have both gaseous as well as liquid values for the enthalpy of formation. What's the difference? Just the enthalpy of vaporization, that's all. There's a problem. Let's go ahead and set it up and solve for it. We have solid carbon at 25 C and 1 atm entering a furnace, operating at steady state and burns completely with 100% theoretical air. So the oxygen and the nitrogen come from air. Let's go ahead and get a balanced reaction equation, part A. So we have carbon plus the oxygen coming from air. So we bring along 3.76 kilomoles of nitrogen for every kilomole of oxygen that's coming with the air. And it's going to combust. The only thing we're going to get is carbon dioxide. There's no water vapor going out because there's no hydrogen in this fuel. It's just carbon. Okay. And then let's balance the carbon, so it's a 1 there. Let's now balance the oxygen, a 1 there. And let's balance the nitrogen, 3.76 N2s, and we're done. Is that okay? You like it? Thumbs up? Does it look good? Did I balance it okay? Is there an error? Good. That's the answer to part A. Continue to read. It burns completely 100% theoretical air. That's what we have. That air comes in at 25 degrees C and 1 atm. So basically everything's coming in at 25 degrees C and 1 atm. The products of combustion exit at 25 C and 1 atm. Determine for part B the heat transfer to the furnace from the surroundings in units of kilojoules per kilomole of the fuel. They're asking us to calculate Q dot, but it's per N dot of the fuel. That's a standard question. You know, heat transfer to the furnace from the surroundings in units of kilojoules per kilomole. So that's what we're going to be looking for, Q dot divided by N dot F. The question is, do I expect a positive result or a negative answer? It's going to be a negative answer. And here is even the value. The answer is going to be negative 393,520 kilojoules per kilomole. Why the negative? Burning coal, or like carbon, that's what they're simulating here, even though coal is not all carbon, is very exothermic. It's going to have heat transfer from the furnace. And to keep the products going out cold at 25, you're going to have to remove a lot of heat out of that furnace. Okay, so here's our general first law. I didn't want to write it down again. This is 0. We have the changes from the 298. This change right here is the enthalpy on a molar basis at the temperature that the reactants are coming in at minus the molar enthalpy at 298, our reference temperature. Well, if the reactants are all coming in at 298, then all of the delta H bars are 0. Likewise, if they're all going out at 298 Kelvin, all the delta H bars of the products are 0. So what do we come down with? We have what we're interested in calculating, Q dot divided by N dot is equal to the sum over all the products. Well, this will be the N times enthalpy of formation for the carbon plus, it's carbon dioxide for the product, plus N times enthalpy of formation for the nitrogen. Then I have minus all of the sum over all the reactants. We have the stoichiometric coefficient times enthalpy of formation. I should put a naught on there. For the carbon as a solid. And we have the N times the enthalpy of formation for the oxygen. Why did I put the parenthesis there? Come on now. Minus N enthalpy formation for the nitrogen. Now I wrote a lot of terms and I know they're 0. Let's strike the ones that are 0. So what about the nitrogen? Its nitrogen has enthalpy formation of 0, as well as it's on both sides. It would cancel that way too, but its enthalpy of formation is 0 for sure. How about the oxygen, O2? We look back at our table and we find, hey, the enthalpy of formation of oxygen is 0. All right. So all we have to do now is put in our stoichiometric coefficient for the CO2. It's 1. Then the enthalpy of formation, negative 393,520 kilojoules per kilomole. And then we have minus stoichiometric coefficient for the carbon, 1. And then the enthalpy of formation for the solid carbon. Well, guess what? That one we don't use that often, but its enthalpy of formation is also 0 for the carbon, solid carbon. And so the answer boils down to, this Q dot divided by N dot F is negative 393,520 kilojoules per kilomole. It's almost anticlimactic. It's all like, wow, all that work to do what? Did you follow that logic? Is 0. Yeah, and so it's this top line right here. Carbon, solid, enthalpy formation, 0. That's where it's at in our table. Okay, let's continue on then. So now we can introduce a new group of terms. It's a little more convenient. It's called the standard enthalpy of combustion. This is the symbol right here, H bar naught R to P. Now, I understand the H, it's enthalpy. I understand it's on a molar basis. I understand it's standard conditions. I don't understand R to P. What's that R to P? From reactants to products. From reactants to products, R to P. So it's our standard enthalpy of combustion from reactants to products. And it's defined simply in terms of the enthalpy of formations. So it's like you took the general energy conservation equation, I just rewrote it, that's the one we just used, and we said, this term and that term times the standard coefficients are always kind of there. Grab them all, put them into one term. That one term is defined as this, give it a name. It's the standard enthalpy of combustion. And now it's just the change from 298 from the products, or the change in the enthalpy from the reference 298 for each of the reactants. Maybe you like this one, maybe you just stay with this one. It doesn't matter, you just have to solve the problems correctly. But it's the standard enthalpy of combustion. What does it depend on? The stoichiometric coefficient and the enthalpy of formation for the standard combustion, okay, of that fuel. Calculate the standard enthalpy of combustion for liquid methanol, assuming the water is liquid in the products. Okay, so we want to calculate what exactly? This term. Isn't that our symbol for the standard enthalpy of combustion? What's it defined as? How do I calculate it? The sum, the stoichiometric coefficients of the products times the enthalpy of formation over all the products minus the sum of the stoichiometric coefficient, standard enthalpy of formation over all the reactants. Did I do that correctly? So now what I have to do is I have to say, okay, give me the equation so I can get those stoichiometric coefficients. Give me the balanced reaction equation for the combustion of liquid methanol. So let's try and tuck it in right here. CH3OH. Every now and then, I encourage you to avoid slippery spots. Every now and then you walk out and you're walking down a hallway and they put a little sign out right in the middle of the hallway. It says, caution, wet floor, slippery, don't slip and fall. True? You ever see that sign? As you get older, you start slowing down and paying attention to them signs. When you're young, you just blaze right on through. Doesn't matter. Because you're so physically fit, you can slip a little bit and catch yourself, like sliding and skateboarding down the hallway or ice skating. But anyway, for a person like myself, I have to go slowly. That sign. Right now I'm going to tell you, warning, slippery, wet floor. Look at that fuel. What's different between that fuel and a lot of other fuels? Between that fuel and methane and propane and octane. There's a big O in it. What is that O in it? Oxygen. And when the students do an oxygen balance on a fuel that has a little oxygen in it, like this methanol, they'll forget that the oxygen, there's one little O in that fuel. And they'll mess up the oxygen balance. So go slow, slippery, warning. Right here, okay? Don't fall. Okay. So let's continue on. Let's get the oxygen with the... And then where's the carbon going to go? We want it to go to CO2. Do I have enough information to get the coefficient right here in front of the CO2 at this point in this problem? Is it a 1? Sure enough. Let's continue on. Then we want it to go to H2O. Do I have enough? I didn't leave enough room. Let me give enough room here. H2O. Do I have enough information to say how many is that going to be? Is it 2 or 4? It's 2. Yeah. Go slow until you get really good at it. And now at this point, can I go back and balance the oxygen? Yeah. Let's count up. How many oxygens do I have right here? 2. How many do I have right here? I add that, 4. Then I come over here and I say, oh, 1 comes from the fuel. I need 3 from the air. And so I know that air brings it in as O2, so I'll take the 3 and divide by 2, and that'll be it. So I need 1.5. 1.5. Does that make sense for the oxygen balance? Did I do it right? What is the common error? Common error, they'll say, oh, I'll just put a 2 right there. All 4 of the oxygens come from the... No, don't do that. Don't do that. Don't do that. 3 halves. That's correct, isn't it? And to finish it out, let's put 3 halves times 3.76 N2s, but the nitrogens aren't all that important. Now let's go ahead and say, for each of those products, I'm going to have 1 times the enthalpy of formation for the carbon dioxide. I'm going to have 2 times the enthalpy of formation for the H2O. Now I go slow because I look down here. There's water, that's H2O, that's H2O, but they have different enthalpy of formations because it could be in the gaseous or liquid state. What did they tell me in the problem statement? Water is liquid. So I'm just going to emphasize L on that one. And when I come down and grab a value out of the table, I'm going to grab that value for the standard enthalpy of formation of liquid water. Continuing on, do I need to include the nitrogen? It's one of the products, but its enthalpy of formation for nitrogen is 0. Then let's go to the reactants. So for the reactants, I have the liquid methanol, so it's going to be a minus 1 times the enthalpy of formation for the CH3OH. I come down here. Oh, there's 2 methanols. One is gaseous, one is liquid. I better grab the liquid value for the enthalpy of formation. True? All right. Then the other reactants are the oxygen, but the oxygen has an enthalpy of formation of 0, and we already said that nitrogen is on both sides. Looks like it's a reactant, looks like it's a product, but it has enthalpy of formation of 0. So this equation is finished. We have 1 times negative 393,520 plus 2 times negative 285,830 minus 1 times negative 238,810, and then you'll get the negative 726,370, the units of kilojoules per kilomole. Each one of these are kilojoules per kilomole, kilojoules per kilomole, kilojoules per kilomole. There you go. So what is this term again? Standard enthalpy of combustion for that fuel, and you really need to know how that product goes out if it's water. Does it go out liquid or does it go out vapor? True? Yes?
So, how come you didn't do it for the night for the you didn't do it for the air, right?
Yeah, the enthalpy of formation of the oxygen is 0,
Oh,
and the enthalpy of formation of the nitrogen is 0. Yeah, the enthalpy. So I could have put them in the equation and said, hey, they're 0, but I'm saving space. Look good? Wow, do we want to solve another one of these? Let's come back to it if we have time. So this table, we go into this table quite a bit, and we're getting those enthalpy of formations in the energy balance equation. Here's a question. Clicker questions. Ready? Are we ready for clicker questions? So the first clicker question is when computing the standard enthalpy of combustion, whenever you have a word like this, it's brand new in engineering, you think, what symbol was that for the standard enthalpy of combustion? Was that symbol, Q dot divided by N dot F? No. It's this. True? That's what we're talking about. Okay. It matters if the fuel is liquid or gaseous, true or false. Does it matter if the fuel is liquid or if the fuel is gaseous? True? It does matter. False does not matter. All right. So it does matter, and that's the example we just had. True? It does matter. It'll change the value, the enthalpy of formation of that one of the reactants, which is the fuel. All right. Let's go to this next question. When computing, the standard enthalpy of combustion, same term, it matters if the oxygen is from pure oxygen or if the oxygen comes from air. It does matter. Yes, it does, then say true. If it doesn't matter, say false. Well, let's take a look. Congratulations. The oxygen has an enthalpy of formation of zip. And if it comes from air, it brings nitrogen with it. What is enthalpy of formation of nitrogen? 0. So there you go. You like these questions? When computing the standard enthalpy of combustion, it matters if the product of water is either liquid or gaseous. If the product, water, is liquid or gaseous. There we go. We'll start it now. That's it. I need to get harder questions, huh? Too easy? That's okay. You like to boost your little clicker score. It does matter because it did change the enthalpy of formation of that product, water. Okay. The standard enthalpy of combustion for liquid methanol is reported in table A25. True, it is reported in there, or false, it's not reported in there. The standard enthalpy of combustion for liquid methanol, is it reported in table A25? Well, let me ask this. If I would have changed that question and I would have said the molar mass of liquid methanol, is it reported in that table? And you'd have said, right there it is, right there, right? Right? How about this? I say the enthalpy of formation. Just get this, enthalpy of formation. Is it enthalpy of formation? Yes, there it is, right there. It's in that column, right there. I said, no, the standard enthalpy of combustion. Oh man, I misspelled that. Combustion, okay? Sorry about the misspelling. Well, where is it? It's not in there. It's not reported there. Why do so many people say, yeah, it's reported there, I can see it? True? Nah, you can't see it.
You mean in distributed formation, actually?
No, it's a standard enthalpy of combustion. I'm looking for H, R, P, bar not. And it's not in there. Okay? And, you interpreted that as formation. That's what you're saying. Okay. Well, the tools are there to compute it. So what are the tools to compute it? You have to get the sum over all the products, the stoichiometric coefficients, enthalpy of formation, minus the sum stoichiometric coefficient, enthalpy of formation. The tools are there. I need to know the stoichiometric coefficients and use those enthalpies of formation. That's what I need to do. Okay. Heating values. Well, what are these two columns over there? You have a higher heating value and a lower heating value. Now, this is what engineers came up with. All right? That's what the engineers come up with. Do you see negative signs in that column? Do you know engineers don't like to walk on slippery, freshly mopped floors? Why? They get hurt when they fall. Well, you know what? Engineers don't like it when they have minus signs, errors in their calculations. It can lead to big problems that cost them a lot of money and may hurt other people that they love. True? And like their customers and other people in the public. So we like to avoid errors. Now, there's a whole bunch of negative signs. That's a sign that it's done by a chemist or a physicist. It is truly. It's like, oh, we just have to live with all these minus signs. No, we want to avoid them because they're error prone. They make us, unfortunately, make a mistake every now and then. So anyway, this is the heating value. So what happens is these also are based on, take a look at the units. Not only the sign is important, but what are the units? Look at the units, kilojoules per kilogram. Engineers, a lot of us just like to work on mass basis, not so much on a molar basis. So what exactly are these heating values? Well, if I take this fuel, let's say methanol, and I put it into a furnace, and I'm trying to combust it, and I bring some oxygen, maybe from some air, so I have some fuel and some combustion air. I'm really interested in what I get out of that furnace to keep my home warm in the middle of the winter, or to drive the process in the plant by burning some fuel. I'm trying to heat something up, get some warm water for some process or some other something is useful. I'm interested in this as a positive, good product out of that furnace. True? And so it's Q dot divided by M dot. That's what it is. It's the rate of heat transfer per unit mass flow rate of that fuel. Now the question is okay, it's kilojoules per kilogram of the fuel. Why do I have a lower and a higher heating value? Because this is burning the fuel on a Monday, and this is burning the fuel on a Friday. Oh, no, come on now. This is burning it in the morning and burning it late at night. No, nothing like that. Why would you have two different values for the heat coming out of the furnace? A lower and a higher. Notice the engineers are not real clever about the names either. Look at the magnitude. What do you think? The magnitude comparison. The higher is greater than the lower. On every one of them? Every one of them. Right? Okay, so what's the difference? No. What did you say? No pressure. No temperature. Let me ask you this. To get the max Q out, what do you assume? First of all, standard conditions on the fuel coming in. What do you think they assume for the products going out for the temperature if they want the maximum 25 degrees C? We're going to talk about adiabatic flame temperature. That means no heat out of the furnace and the products come out spanking hot. Well, great, you burned something, but you didn't get anything out of it. You just put up hot exhaust gases out the flue. You put out 25 degrees C out the flue, you got the most out of that fuel. You got most heat out of that fuel. So that's what's going to be the heating values are both, they're all going to be coming out. Both of these values are 25 degrees C for the products. The products at 25 degrees C, the products at 25 degrees C. So it's not a difference in the temperature of the products. But why is one high and one low?
Is one 100% oxygen and one air?
It's not necessarily where the oxygen comes from. Because the nitrogen is just tagging along. It came in at 25, it goes out at 25. Those are good observations, good tries. Don't give up on me. Try another one. You're not going to have excess oxygen or deficient oxygen, and every bit of that fuel is burnt. It's complete combustion.
The state of the fuel?
The state of the fuel will be taken into account. So if I say it's gaseous methanol, you have two different values, higher and lower heating value. If I say it's liquid methanol, you have two different values for higher and heating value. That's it. Bingo. The state of the water that's coming out. The water can come out at 25 degrees C either as G or V or L or something. It's gaseous or liquid, okay? Okay, so if it comes out gaseous or if it comes out liquid, that's going to have an impact. Now, so take your pick now. The higher heating value and the lower heating value. Which one, how does the water go out? Does the water go out? Let's ask a clicker question. Answer A or answer B? The water goes out either as vapor for the higher heating value or liquid, or switch them, liquid for the higher heating value and vapor for the lower heating value. This is a clicker question. The difference between the higher and the lower heating value has to do with how the water leaves as one of the products. If it leaves as a vapor, does that mean that that's going to give you a higher heating value? Or if it leaves as a vapor, does that mean it gives you a lower heating value? Which one is it? More time? Okay, got more time. All right. Well, let me ask you this. Let me try and avoid this AB. Let's try and break it down even earlier. If the water goes out in the liquid state, does that mean that it would, normally if you're burning something, combusting something, it's going to go out in a vapor state because the products are pretty warm. But we said, look, we want the most heat out of our furnace, so let's cool the products to 25. How are you going to cool it? By pushing more heat out of the furnace. Q dot is increased by making this temperature as low as possible. The lowest reasonable is 25 degrees C. See how Q dot is increased? I get a maximum heating value if I say the products go out at 25 C. Same line of thought. If we say the water goes out, liquid or vapor, if I want more pushing of heat out of that furnace, how should the water go out? Condense it. Condense it. It's going to have to push heat out of the furnace, right? Q dot will be larger if it goes out liquid. So the highest of the heating values, the higher heating value, will mean that the water goes out in the liquid state. Okay? So true? All right. So if it goes out in the vapor state, well, it's a higher energy for that product going out, and so you get a lower heating value. Well, how do we jump back and forth between the heating values and the enthalpy of combustion? Well, the enthalpy of combustion, and you pick your fuel, is it liquid methanol or gaseous methanol? Okay, one of those lines we're going to have to get on, is equal to, I need a negative sign because engineers took that heating value, and they made it positive, so I'm going to have to make it back negative for the enthalpy of combustion. And they had it on a mass basis, I need it on a molar basis, so multiplied by the molar mass of the fuel. Now you say to yourself, enthalpy of combustion, either I pick the lower heating value or the higher heating value. It did matter for both of those. So you just have to be like, which value? Probably the higher heating value. If you do that, then the water in the products goes out as liquid. Or if you say, no, I want the lower heating value because I'm going to be using that the water in the products goes out as vapor. Great, there you go. Okay? All right. When computing the heating value of the fuel, it matters if the fuel is liquid or gaseous. Might as well just boost up our clicker scores today. Well, to answer that question, pop right back here and say, I have two fuels, do I not? Do they have the same higher heating value and the same lower heating value? They don't. So it must matter. It does matter. Yeah, it does matter. All right, let's try and continue. When computing the heating value of a fuel, it matters if oxygen is from a pure source of oxygen or if oxygen comes from the air. The heating value, when you compute the heating value, it matters if the oxygen is from pure oxygen or if the oxygen comes from air. Well, the oxygen basically is just going along for the ride, And if it comes with air, it brings along nitrogen, but both of them are coming out at 25 C. Nitrogen didn't heat up at all. So there's no, it does not matter where the oxygen came from, with or without nitrogen. Last question. When computing the heating value of a fuel, it matters if water in the products is liquid or gaseous. Well, I didn't make these questions to be tricky, but 5 people are confused, and I don't know exactly why. Well, it does matter. It changes the heating value. That's why you had a lower heating value and a higher heating value, right? It's how the water went out in the products. And how do you get the highest high heating value? The higher heating value, water goes out at the lowest energy state, goes out liquid. Most of the time, water's not going out. Our flue is liquid water. When we burn it, we're creating some water vapor in the products, and it goes out in a vapor state. But you do have a higher heating value. It's harder to achieve, and we'll talk. Did I already mention about condensing furnaces? This is an oxymoron. Condensing furnace. Anybody ever heard of a condensing furnace? You're going to burn propane or methane in your house, and the furnace is going to condense. What's it going to condense? The water in the products that come about by breaking up that hydrocarbon fuel. You get CO2 and you get water vapor. Engineers have tried to make high-efficiency furnaces so you don't have to burn and pay for as much methane or natural gas in the winter to keep your house warm, true? And so the highest of the high efficiency would be, try to squeeze all that heat out of the products and get it into the house to keep the house warm, not just send hot gases out the flue. You ever see homes with their furnaces running in the middle of winter and very cold state up north? That just nice little wisp of hot gases coming out, and it condenses with the water vapor when it hits. It's like wisping a little white. It's like, well, you're trying to heat up the outside, but you want that heat inside your home. So they make condensing furnaces, and the first time you hear it, you say, what was the engineer thinking that designed and proposed that? But that's the highest efficiency furnace. And they'll actually try to take that products out at 25 degrees C, or is that cold, which means they have to condense because it's below the dew point temperature. And when they condense, they get more heat into the home. Where does that water go? Well, they can collect it, and guess what? In the middle of winter, if your outside air is really cold, it's also dry, very dry. You ever had static friction problems in your houses in the middle of winter? You just walk around, you touch the doorknob, jeep. In the summer, do you have that problem? You ever get static electric shock touching the doorknob at your house after you walk across carpet in the middle of summer? No, it's not dry at all. It's humid. You just sit there and sweat. But in the winter, it's dry. So guess what? Heat in the house, great. A little extra water vapor in the house, no sweat. No problem. A lot of homes up north have humidifiers, not dehumidifiers, humidifiers to add liquid water to spray it into the home to try and get it moist because the skin gets dry, static electricity problems, and your nasal passages dry out. If you ever had that, anybody been where the nasal passages dry out and they crack and bleed? Yeah, it's very annoying. But you go to some really cold place. Maybe you go to Alaska in the middle of winter, right? Anyway, anybody been in the Air Force? They sit you out in the islands in Alaska in the middle of winter. Aleutian chain. Just sit there in some Air Force base listening, see if any bombers coming from Russia. That's what my dad did for a number of years. That's what I'm sure a bunch of Air Force guys are doing right now, waiting for winter. Sitting out there on a chain. Okay. But yeah, it can be very dry and annoying and get nosebleeds, as well as lungs and everything else. Feels bad. I'm going to try and solve some more problems later. And I'm going to skip that problem. Let me move forward. Hey, where's my file? Let's talk about adiabatic flame temperature now. Now, instead of trying to get all the heat out of where the combustion's occurring, think about this as a control volume where the combustion's occurring, and it's adiabatic. How much heat do you get out of that? Nothing. So here, Q dot divided by N dot of the fuel is 0 in our energy balance. And what happens? All that energy that's released in the combustion makes the products, this is the products coming out right here, spanking hot. Well, how hot is spanking hot? Well, the hottest it gets is the adiabatic flame temperature. And now you are equipped with the tools to calculate the adiabatic flame temperature of that fuel. Different fuels combusted with air, the perfect amount of air, not too much, not too little, just 100% theoretical air so that all of the fuels combusted have different adiabatic flame temperatures. Some fuels are really hot, some are not so hot. Okay, so we start with energy balance applied to this control volume, adiabatic. Again, there's no work. It's very rare that we have that term is not 0. Most of the time it's 0. We have whatever is the fuel, and it has a different heating value or a different enthalpy of combustion. We bring in all our reactants typically are at 25 degrees C. So we're not bringing in the reactants hot or cold. We're just bringing them in at standard conditions. Then we can compare apples to apples. Does your fuel burn hotter than this other fuel or not? And this right here is where you have the adiabatic flame temperature. It's the sum of N, the stoichiometric coefficient, times the molar enthalpy evaluated at the adiabatic flame temperature minus the molar enthalpy evaluated at our standard condition. That's our delta H. So we sum over the products. So there's our energy balance equation used to calculate the adiabatic flame temperature. If the percent theoretical air is increased, so we used to have 100% theoretical air. Now it's 110, no, 120, 130, 150%. You're bringing in more air, right? How does the adiabatic flame temperature change? Will the adiabatic flame temperature increase? Or will it stay the same? It doesn't change. Or will it go down? Will it decrease? Will it decrease? I think you're equipped with enough tools and resources to answer that question. Okay. You got the book in front of you? Professor, it doesn't help if you give me more time. I don't enjoy this uneasy sense of pain. What we're going to do is we're going to have the energy balance equation. This term is 0, this term is 0, all the reactants are 0. And we talked about how excess air, will excess air change the standard enthalpy of combustion? No. So this is unchanged. It doesn't matter, it doesn't affect it because look at the formula again. We answered those questions. It doesn't change that part of the equation. But here is where you have the adiabatic flame temperature. It's h bar of the temperature adiabatic flame minus h bar of 298. That's at delta H. And that's for each of the products. True? Okay. Let's think about going back to our combustion equation for some fuel so we can put some numbers and look at it. Pick methane because it's so easy. Okay. We're going to have O2 plus 3.76 N2. You get really good at balancing this, do you not? 1 CO2 and 2 H2Os, giving you 1, 2, 3, 4, needing 2. And we're going to do it with 2 times 3.76 N2. Does that make sense? Is that now balanced with 100% theoretical error? But now we're going to say it's 110%. So it'll be, I didn't leave enough room. Let me see if I could scoot this over just a little bit. Just move it over. Perfect. And then come in here and I'm going to say plus 1 plus phi. What do you mean 1 plus phi? Well, it's phi. That's that percent excess air. This is the percent excess air. So if phi is 0.1, then I have 10% excess air or 110% theoretical air. Make sense? So if phi is 0.2, what is my excess air? 20%. It's 120% theoretical air. Okay? Well, then I'm going to have 1 plus phi go for the ride on the nitrogen. And for the oxygen, I'll have phi times 2. Does that make sense? Why do I have phi times 2 for the oxygen? Because the 100% was used to go to make water vapor and carbon dioxide, but the excess phi just went through the ride, through the system. True? So when you have excess air, when you have increased amount of air above, you get more nitrogen and some unused oxygen. Would you consider everything on this side a P, a product, so that it comes in here? Would this carbon dioxide go out at the adiabatic flame temperature? Yes. Would this product of water vapor go out at the adiabatic flame temperature? Yes. Would this oxygen that wasn't combusted go out at the same temperature, the adiabatic flame temperature? Yes. Would this nitrogen go out at the adiabatic? Every one of those products is going out at the same temperature. It's all mixed up combustion products, true? So it's going to take more energy. Just think about the nitrogen, then the excess oxygen. They kind of like were just leeches. They just went along for the ride. And they went, oh, it's a free lunch. You know, I'll go to the restaurant with you if you're paying. And they took a bunch of the heat of the combustion. And so they brought down that adiabatic flame temperature. Excess air reduces the adiabatic flame temperature. Ready to have it graded? What? Calculate the adiabatic flame temperature for propane with 100% theoretical air and then 200% theoretical air. Which one is going to be higher? The first one. And then the 200% theoretical is lower because a lot of nitrogen went along and got heated up. More of it. And then there's a little bit of excess oxygen too that just went along and got heated up as well.
The first 100% is just 1 plus V equals 0, and the second one is 1 plus V equals 1?
Well, let's write it out. So we have the C3H8, and I'm going to put a 1 plus V, and I'm going to leave a little room for the balance on the O2 plus 3.76 N2, and now we're going to go ahead and see how many carbon dioxides do I get when I burn propane. 3. And then how many water vapors do I get when I burn propane? 4. Now I look and I have 6 and 4. 6 and 4 is 10. So I'll need 5 O2s. I make sure there's no O tucked in here with the fuel. I don't want to slip on that wet floor and hurt my head. And then I come out and I say, now I'm going to have phi in general. And now I'll have phi times 5 O2s. And I'll have 1 plus phi times 5 times, oh, I didn't leave enough room. Oh, come on now, let me try again. 1 plus phi times 5 times 3.76 N2. Does that look general? Good. Now, for the first case A, what should phi be? 0. And for the second case, what should phi be? 1. You're good, you're good. This is great. All right, so now, if I want to calculate that adiabatic flame temperature for propane, the energy balance equation goes down to sum over all the products, the stoichiometric coefficient, the change in the enthalpy. True? So it's going to be, let me do it this way, 0 is equal to the enthalpy of combustion plus, and then I'm going to have 3 times the enthalpy at the adiabatic flame temperature minus enthalpy at 298 molar basis, and that's all for the CO2. Then we'll have 4 enthalpy at the adiabatic flame temperature minus the molar enthalpy at 298. Another parenthesis. Boy, I got a lot of parentheses. H2O plus, then I come down here because I'm going to need more room, plus phi times 5 times the molar enthalpy at the adiabatic flame temperature minus the molar enthalpy at 298 for, oh, I lost track of all my parentheses, 4 oxygen, and then 1 plus phi times 5 times 3.76 times the molar enthalpy of the adiabatic flame temperature minus molar enthalpy 298, close, nitrogen. That makes sense? Makes sense? All right. So where's my unknown that I'm trying to solve for? Right here, right here, right here, and right here. You mean that's the same temperature? Yep, because the CO2, the water, the oxygen, and nitrogen all go out at that high temperature that we're trying to calculate, the adiabatic flame temperature. If I want to do a great job of solving for this, I want to use this table A23, which gives me the ideal gas properties of selected gases. When every one of those products goes out as a product, it's going out as an ideal gas. And so that's why they give us the carbon dioxide column, and I'm interested in H bar. That's why they give us the water vapor column. I'm interested in H bar, this H bar. The oxygen as well as the nitrogen. So I would use this table, and I would use values especially at 298 temperature. That's our standard. We're going to be always subtracting that off. And then I have to say, does it come out at 2,000? Does it come out at 3,000? What temperature does it come out at? Make sense? All right. Should I give you some numbers on this one so you could play with it? Let me see if I have the numbers. I know I do. So if we do it for theoretical air, what I'm going to have is an equation that I want to set equal to 0. The first term in the equation is that can't write. That standard enthalpy of combustion for the propane. Okay? That standard enthalpy of combustion for the propane. And then what do we have? We're going to have the 3 times. Now, I have to pick something. I'm going to pick for the first one that it goes out at 2,000 Kelvin. I just have to assume that because I have to iterate. There's no easy way to use this table without iterating when I don't know the temperature at which I need to get the enthalpies at. So this would be the enthalpy of carbon dioxide at 2,000, 100,804, minus the 9,364. That's the carbon dioxide. Then we had how many water vapors? 4. And then what did we have for the standard enthalpy at 2,000? 80,2593 minus 9,904. And then for the oxygen was 0, so I'm going to leave that off. But for the nitrogen, we had 5 times 3.76, which is 18.8, times the value at 2,000, 64,810, minus the value of the enthalpy, 8669 at 298. All right? So, what was the value of the standard enthalpy of formation for that fuel? I forgot to write it in here, but it's negative 2,044,000, close enough. I mean, I can get more digits on it, but that's close enough. 4 significant digits. So, is this function, it's a function of the adiabatic flame temperature. I'm picking it to be 2,000. And when I evaluate it, unfortunately, it's not equal to 0. It's equal to negative 423, 463. All right? So now let's pick a different value. Let's pick 3,000 and rerun it. So we'll say the function that I want to be equal to 0 when I pick 3,000 is equal to negative 2,044,000, the standard enthalpy of combustion, plus 3 times, then I'm going to use this value for the enthalpy at that elevated 162,226 minus the same value, 9,364, plus then 4 times for the water vapor, 136,264 minus 9,904 plus 18.8 times 101,407 minus 8669. And when you get that, you say, oh great, it's now 663,500. This is above 0, where before it was below 0. I'm hopeless. This is terrible. I want it to be 0. But I picked an adiabatic flame temperature 2,000. It wasn't 0, it was negative. I picked an adiabatic flame temperature 3,000. It wasn't 0, it was positive. So what do you do now to get the better estimate of the adiabatic flame temperature? So when you interpolate, you get a better estimate of the adiabatic flame temperature. It's 2390 Kelvin. Shoot for a value that you might think is ridiculously low, 2,000. Shoot for a value that's ridiculously high, 3,000. Usually you bracket, interpolate. Even if you don't bracket, you can still interpolate. It's called extrapolate outside of the range. It's still going to be very accurate. Now you take a look at Wikipedia and you say, hey, I think I'd like to know what the adiabatic flame temperatures are of some common gases and materials. Hey, did we just do this for propane? Hey, did we just do this for burning in air? 100% theoretical air. Hey, what's this? 1980, 2390 Kelvin. So we want to take 273 off. And we get 21, I'm going to round off to, 20 degrees C. Hey, how come that's higher than this value of 1980? What gives? I'll write them a letter, tell them to fix their problem. No. The adiabatic flame temperature that we predicted is higher than experimental measurements. These are basically experimental measurements because there's not complete combustion in any combustion system. A lot of them are better than others, but there's incomplete combustion. Often, to get complete combustion, you need a slight amount of excess air. We did perfect amount of air and complete combustion in our calculation. And there is heat loss. That blue flame, why is it blue? Why can you see it? There's photons coming from it towards you. If I turn out the lights in the room and I look at the flame, is it still blue? Because it's hot and it's emitting a radiative energy, and that's cooling it. And there are some disassociation. When you start to really get high temperatures, it doesn't just like to stay as CO2. Even though it may have complete combusted, it may want to disassociate. And maybe the nitrogen in there just doesn't go happily along as nitrogen. It likes to kind of go to an NOx, which is an oxide of nitrogen. And that's that brown haze you're going to see today out there. Summer days, you get inverted automobiles. They put out NOx. It reacts at the ground level, and you get haze in the summer in cities like San Antonio and Houston and other Dallas. Anybody know what I'm talking about? Ever seen it? You don't get it in the winter. It needs that intense sunlight for a chain reaction for the ozone to go. In the inverted temperature, and it's still day, not a heavy windy day, which sweeps the stuff to your neighboring counties. All right, so that's why these adiabatic flame temperatures are not the same as what you would predict using the tools in our textbook. Now, we have mastered energy balance. Now we want to master entropy, second law calculations for reacting systems. Well, second law, you would say, the rate of change. First of all, no transients. They just give up on that. Like, forget the transient part. Steady state, flow through control volume. There can be heat transfer into the control volume as well as negative in, which is an out, taking with it entropy. You would divide by the steady boundary temperature, and there is a way of calculating the entropy transfer with heat transfer. You have all of the reactants bringing in on a molar basis, and all of the products going out on a molar basis, plus what's this? Irreversibilities. So there's our entropy balance equation, their second law. How do I calculate things like this? Entropy of each of those constituents. Oh, just like I had to calculate enthalpy for each of those constituents. Well, each of them are behaving as ideal gases. I'm not introducing, the textbook does not introduce the tools to allow you to do it for real gases or two-phase liquid vapor mixtures and stuff like that. It's all just ideal gases. Now, we're going to have a fuel that can come in liquid. That's the one exception. But we're not going to have the fuel come in liquid at anything other than standard conditions. If it's going to come in liquid, it's standard conditions. Okay. So let's take a look at this form of how you would evaluate this molar entropy for each of those constituents, be they on the reactant or on the product part. Look, it's a function of temperature and pressure. Is that a typo? Is that a typo, or should it be the molar entropy of a constituent is a function of temperature only? Hey, the enthalpy was a function of temperature only. Is there a typo? Is it a function of temperature and pressure, or temperature only? Temperature and pressure. This is what's really different and more difficult for entropy calculations. Enthalpy, temperature only, ideal gases. Entropy, temperature and pressure. And the pressure shows up in this form right here. Does that look familiar? The natural log of P over P ref, natural log of some partial pressure in that mixture divided by the reference pressure? Yes. So we have this is the temperature dependent component, this is the pressure dependent component to calculate those entropies. Well, we're introduced to a third and final law. We had the first law, conservation of energy. Second law, entropy balance. Basically, you can't just willy-nilly transfer energy between forms. There's limits on the transfer of energy between forms. And the third law, the absolute entropy of a pure crystalline substance is zero at absolute zero temperature. 0 Kelvin? Yep, 0 Kelvin. We're never going to get there. I know it's theoretical. So basically they say we need to have something for putting everything on the same entropy calculation basis. And so they introduced this third law with concept of absolute entropy. Why pure crystalline? Pure crystalline has no uncertainty where its neighbors are. You go this way and there's a neighbor, that way there's a neighbor. If it's an amorphous solid, it's like, where are my neighbors? I don't know, they're somewhere around here. So crystalline is all regularly laid out. 0 Kelvin, how much wiggling, jiggling, and motion is there at the molecular level? 0, it's dead stop. That's why you have it. Crystalline, pure crystalline substance, 0 Kelvin. Gives you no uncertainty, and hence no absolute entropy is set to 0. Is it possible to get there? No, it's impossible to get there. So now we can take a look at this column right here. They said, look, starting there, we can then estimate or calculate and report the entropy of, let's say, oxygen in the gaseous state at 1 atm and 25 degrees C. There it is. Professor, I'd like you to prove to me this number 20503. No, I can't do that. It's in the table, okay? We know how it's related to other things. But every one of these now are related so that when that oxygen gets paired up and now participates in the carbon dioxide, and that carbon gets paired up and participates, that this is related to these and these values, okay? They're all on a common entropy basis as long as you have this absolute entropy. Professor, we then look at this table A23, okay? Look at this column right here. We had the H bar, we skipped the U bar, and now we're looking at that S bar naught. Is that data right there? Yep, sure is. So if you look at this carbon dioxide table, A23, at 298, look at this number, 213. Do I see that number anywhere else? Sure enough, they're consistent. Wow, isn't that great? The textbook's consistent, such that for the carbon dioxide in the gaseous form, the absolute entropy at 298 1 atm is, got it? Let's take a look at this water vapor. Water vapor, 188.72. Is that number anywhere else in this table A23? It's in that table A25. It's right here. You could do the same thing for the oxygen. Here's the oxygen value, and there's the oxygen value. All right. You could also do it for the carbon monoxide. Carbon monoxide. There's a lot of this chapter that we're not covering. The chemical exergy is not being covered. So a lot of that is gone. But we did cover the absolute entropy in the third law of thermodynamics. That's all good. For reacting systems, entropy and entropy balances. We did not do evaluating Gibbs function for reacting systems. No Gibbs function for reacting systems. All right. What about this fuel cells? I just wish there was more time to cover all these topics. How about using computer software? I wish I had time to give you a project, but no computer software is used. But the rest of it is yes, yes, yes on the adiabatic flame temperature, conservation of energy for reacting systems, enthalpy of combustion, heating values, all that yes, yes, yes. And just what are fuels and modeling air and products of combustion and getting that balanced reaction equation. All yes, 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 yes. Does that help?
What about flow systems for entropy?
Which section is that? This is a no here.
Right before Gibbs.
Entropy balances for reacting systems. This one?
That includes open and closed?
Oh, yeah. No, skip all closed. Closed, no. Okay. Only open. Only open systems, okay?
Close would be like combustion.
No, it's more like a bomb calorimeter.
Okay.
You put a little of this, a little of that in there, you seal it, it's rigid, and then you blow it up. Yeah, we have the tools to do it if you have time, but in the interest of time, we have to skip it. So it's flowing in and flowing out. We're really not using those U-bars on our tables. I've never really spent time on the internal energies, which would be needed for a closed system. And we're just using it for H-bars, the open system, enthalpies. Okay? Thank you for that question. Any other questions? Thank you for your attention. We'll see you next week